ओके तो इस टॉक का आइडिया बेसिकली है कि बहुत सारे लोगों को कितने लोग यहाँ पे डेटाबेस मतलब मेंटेन करते हैं, ऑपरेट करते हैं, रेज अप हैंड्स। कितने लोगों को अंडरलाइन थिंग्स के बारे में पता है, एफ सिंक क्या होता है? किसी ने सुना है एफ सिंक क्या होता है? नो वन? ओके सो the idea of this talk is to understand why databases work the way they do and how they work internally. So I was recently working on Elasticsearch quite a bit, so I just chose this topic, just covering Elasticsearch under the hood. I really feel like still I have more to add to this. This already has 70 slides, but yeah, let's start. Okay. So a word about big data. कितने लोग यहाँ पे मे बी पेटाबाइट्स में मैनेज कर रहे हैं डेटा, टेराबाइट्स में नहीं, पेटाबाइट्स में. So when the data gets bigger and you have to manage your systems to maintain that data at a large scale, what do you think a strategy could look like to manage that big data? So once, like many people, what they do is, and what most of the systems have evolved to do is, they treat that this big data as one, and they divide a lot of chunks, a lot of parts to it. Some databases call that sharding. So you have one data split in different shards. Some databases call it, I mean, it is known by different names. So big data, Elasticsearch is one tool to manage big data. Maybe in petabytes, so we are managing in terabytes, 2 petabytes, you can see. Distributed systems. So if you have a cluster of nodes of one system, and one node goes down, or maybe you have applications, multiple applications, and to which node should they communicate to fetch that data? Maybe any node can go down, any system can fail. So the idea of distributed systems is to acknowledge that any system can fail at any point, and even if the failure happens, the system continues to operate as smoothly as possible without any disruptions to the business. So it does not matter to which node the application connects to fetch that data. The data will be given to the application regardless of the failure happens or not. So yeah, does not matter which node you are connecting to. Massively parallel processing. So you have your data split up into multiple nodes of one cluster. How do you think the most efficient ways to query that data? Because you are now split and you are now replicating across multiple nodes your data. So you can now query parallelly to multiple nodes because your data is split. Massively parallel processing's idea is that you can build a distributed system, not hold your data on one node, that there is no one primary. The data is divided across all. There's no concept of that, okay, this all data will be served on this from this node only. Data is spread across all. You can query all, and you can query all in parallel, right? So this is what MPP systems, massively parallel systems, allow you to do. You can parallelly query across all nodes, increasing the efficiency, the throughput, and decreasing the time. So systems can be organized into two major things, two major categories: monolithic and distributed. Monolithic systems architecture, if we go from a theoretical perspective, it holds shared memory architecture whenever you go into the theoretical side of it. So shared memory architecture's idea is that you have multiple processes, but all those processes have a shared memory through which they are fetching instructions and data, because memory holds what? Instructions and data. So if you are having a system that is monolithic, you can call it, or in a theoretical aspect, you call it a shared memory architecture. because all processes are sharing one memory. They are fetching instructions from it, they are fetching data from it, and then processing it. In a distributed system, it divides into two categories. One is shared disk, and one is shared nothing. So Elasticsearch falls into the category of shared nothing. What shared disk means is, if you have worked on big data systems like Trino or Presto, has anyone heard of Presto, Trino over here? Exactly. So in AWS, people might have heard of Athena, right? So that is an implementation of that they have absorbed and maybe modified it a little bit, the Presto engine part at their end. And what Presto and Trino basically do is they separate out the compute layer from the storage layer. So you have multiple nodes in your compute layer, and the storage layer is shared. The storage layer, you can have your data lake, which is S3. It can be powered by AWS S3, it can be powered by Ceph, Minayo, doesn't matter. But the storage layer is shared. The compute is separate, the storage is separate. So whenever you want to process any data, all of your nodes can fetch in parallel data from this shared storage and process them in parallel in different nodes, and then return the result of the processing back after all of the computation is done. The shared nothing architecture, on the other hand, what it communicates an idea is that you do not separate out storage layer and compute layers totally in different clusters. What you do is you form a one cluster and you create multiple nodes. Each node has its own memory, has its own compute, and it has its own storage. So you will install maybe 100. You can set up a 100-node Elasticsearch cluster, and each node has its own compute, has its own storage, and the data is replicated across multiple storage. There is no separate storage layer as it was in the S3 paradigm, in the shared architecture paradigm. Okay, inverted index. So the idea of inverted index is that you can have multiple strings or a lot of data, and you can index each word separately. So if I have 3 documents over here, and I need to create an index on it, the inverted index would look something like this. And because most of the queries do not matter if there is stop word list, if is not, and whatnot. So they just skip that those lists. Full stop, comma, doesn't matter. If you want to search data, stop words do not matter to you. What matters is at the actual words, the actual data. So the inverted index, what it does is it identifies all the unique tokens, token being each word. It identifies all the unique tokens from all the documents that you are creating an inverted index of. It creates a list. It is basically not a list, a hash map, you say. It creates a hash map where on the one side you have a unique set of tokens, unique set of words, and on the other side you have an array which is referring to the document in which that token or that word exists. So Elasticsearch works on inverted index based on the facility that is provided to it by Lucene. So we'll come on to it. Lucene is a library, Java library that allows a program to create inverted indices and manage them, maintain them, query them. But it is an embedded library, and programs can use them in their own local scope because it is embedded. But what Elasticsearch did was they adapted the Lucene library, which was embedded in its nature, which had local scope, and they created a wrapper on top of it. So you have Lucene, which provides you the facility of creating inverted indices and search them efficiently, your data, and you create a wrapper on top of it, which is Elasticsearch. And now you can create a cluster of these wrappers which can communicate with each other. so data can flow between each node, and the data is managed locally. I mean, it is offloaded, the handling part of it, to Lucene, right? So yeah, Lucene is written in Java, so there's no doubt that Elasticsearch is also written in Java because it is using the wrapper. Okay, so this was about Elasticsearch, horizontally scalable. You can scale it linearly. You add more and more nodes. It scales linearly. So we are currently managing a 100 node cluster, Elasticsearch cluster. So might be we can scale it up a bit more. We do not want to test it out, so we want to keep it a bit under control. But yeah, 100 nodes is what I have seen. Okay. Basic data spread overview. So, as I was talking about the data spread in a distributed system to be able to query it parallelly, massively, what Elasticsearch does is it creates an abstraction which you call index. So many people say that, okay, it is like a table in relational database. Do not think of it like that. You can think of it like that is you have one data, and in that data set you create maybe three shards or three parts of it, and you allocate those three parts to different nodes, and each part you label as index name. So first part is labeled as index 1, second part is labeled as index 1, third part is also labeled as index 1. So any query to index 1, write or read, gets spread to these three parts that are allocated to different nodes, right? So index does not actually exist in a physical form. It is just a logical abstraction on top of the shards. And shards are what actually? Any idea? In implementation, shards are actually Lucene index. So I told you now that Elasticsearch, what it is doing is it is creating an abstraction over on top of Lucene, right? So every shard is nothing but a Lucene index. Exactly nothing, just a Lucene index. And those Lucene indices are can be primary or replica. So P denotes as primary, R denotes as replica. A replica cannot be allocated on the same node. It has to be allocated on a different node. Okay. This is another overview. Elasticsearch shard, one shard which is actually a Lucene index, and in Lucene indexes we'll come ahead forward what segments are and how why do they exist in the first place. Okay, we are starting from the bottom up. We'll come back to Elasticsearch now later. Now we are getting deeper into the storage systems. The challenge of reliable storage. Hard disk or SSD does not matter. Both are equally unreliable in long-term storage. Both can fail, and you need to ensure that how even if failure occurs, then no data is lost. So disks have controllers, and they look like this. This is a hard drive, and it has a disk controller. This is a MMC drive, NAND, and this is a disk controller. And disk controllers have caches in them. Caches in them, like which is outside the scope of operating system, right? So operating system managing its own cache, and the disk, on the other hand, the controller part of it is managing its own cache, right? The operating system does not have any control of it. So how do you imagine that any write that the operating system thinks that it has been done reliably? Because what if the disk fails and it was in cache? What if it fails, right? Disk IOPS are slow. These are some numbers, latency numbers, in reference to the nanosecond latency that each operation takes. So if we talk about L1 cache, just 0.5 nanoseconds. If we go to L2, it reaches up 7 nanoseconds. These are some numbers published by Google actually. So Google SRE team. You can search them online as SRE flashcards. Reading 1 MB sequentially from memory, 250,000 nanoseconds. See how much of a big difference it is making. Reading 1 MB sequentially from SSD, 1 million nanoseconds. SSD, 1 million nanoseconds. Right? Reading 1 MB sequentially from disk, 20 million nanoseconds. Okay. Most databases rely on file systems, not use disks directly. So you must have been working with file system XFS, ext3, ext4, and whatnot. Whenever you install your operating systems in any Linux distribution, I believe you must have mounted the data directory that, okay, this needs to have separate data directory. What is it? It is nothing but a mount point, and that mount point has a file system, right? And file systems have their own metadata to maintain. So if you think about it, what kind of metadata do file systems manage? They manage inode numbers because inode is the thing that file systems identify as what is linked to what and where should I fetch it from. The access time, modify time, change time, birth time. So whenever a file system tries to write something in it, the file system tries to update access time of it. So think of it like this: a database is running on top of your file system. It has its own rights, right? It is writing, and then on each what is it writing? It is writing data, right? But the file system is treating that data, writing it, and then attaching a metadata to it. So the rights have amplified. So it has become more right. The rights have become more just by going from above layer to low, like just by going from one database right to at least two data rights, two rights on the disk, because you're updating data and then you are updating metadata, which means exactly more rights per unit data. The more data you write, the more rights you will. An operating system have their own page cache as well. So whenever you are, whenever any application is writing anything, it is writing it not directly to the disk, but it is writing it to the page cache. Whenever a write call is happening by any application database or any of your application which is writing logs as well, right? So before reaching the file system, those data points, those data elements are cached in the operating system page cache, and then later on flushed. So we have databases, operating system with its cache running, and then on beneath it, we have file system, disks with their own cache outside of control of operating system. Okay, coming on to cache writing policies. You have any questions about it now? This is going very wide because I'm building from the bottom up, because to ensure that to communicate that how databases work reliably and how they do it. Any questions up until now? Am I making sense? Okay. Cache writing policies. So now that we have written the data to cache, how do you think the data is being synchronized or data is being written down onto the storage medium, the disk or SSD or hard disk drive or flash disk, whatnot? There are two policies that work. There are two mechanisms by which you can ensure that data is getting written from page cache to the storage layer. One is write back and one is write through. What write back means is that you write your data to page cache asynchronously. You write it and then you forget it. And now there's some other process that comes up that picks up that data from that page cache and then writes it down to the storage medium. This is writing back. You have written that data and then now you are writing back again to the storage medium. You are written where? Page cache, OS page cache. There's another mechanism that is write through caching policy. So write through, what it means is that you want to skip the page cache. You want to ensure that if my application has written something, then it has persisted on disk. It has not gone to the page cache, because if my operating system crashes, page cache will lose like all of its data because RAM is non-volatile. Volatile. So in that case, I will lose my data, and I want to ensure that all my databases, whenever they are saying that the write has been successfully committed, so the durability is ensured, the asset properties are ensured. There should be no possibility where my database tells my application that I have written, and then later on, when my system fails, the data is lost because it was written to page cache and the writing mechanism was write back and it was not write through. So databases, what they try to follow is the write through mechanism, not the write back mechanism. Linux has this process. If any of you is running Linux on any of your systems, even right now, or maybe you can go back on in the home and check. There's a process, Linux thread called write back, that is always running. This is spawned by kthread-d, that is the Linux kernel, which is kernel's background thread. And this is the actual process, background process, that actually flushes the OS page cache and writes the data from OS page cache to the storage medium, flushes it. And it runs in intervals, right? So how does the database guarantee a write in that case? Because as we have communicated, it cannot use page cache and write back. There's a thing called syscalls in Linux, where anything that you do in operating system, any application that it does is, it communicates either transparently or, I mean, you can directly call syscalls, or other libraries will be calling syscalls for your application. So there are two syscalls, fsync and fdatasync. These are used for write through mechanism. This process was write back, and these syscalls are for write through. So whenever an application has to make sure that a data is being written directly down to the disk, it uses fsync or fdatasync. What are the differences between fsync and fdatasync? So fdatasync, what it tries to do is, it tries to avoid any metadata writes. It only ensures that all data is being written down to disk, because metadata, even if the metadata is lost, it does not care that, okay, we can lose metadata, but we need data on disk. What fsync does is, fsync ensures that both data and metadata are written down to the disk. So fsync is relatively more heavy, but it is very reliable. So yeah. How does it help in guaranteeing a write? As we communicated, by ensuring that everything gets done to the storage layer. In databases, we have CRUD. Every one of you must have known create, read, update, delete operations. And they need to handle create, update, and delete. And each create, update, and delete can result in multiple writes. Let's say you write one row, you insert one row. There is an index that column that in the table that you have written, one column has an index created for it. So there will be one write to write that row in your table, one write to create an entry in the index, maybe there is a trigger also that you have associated in your table. So then there will be another trigger that will be executed. There is another write might be associated to it. There might be foreign keys, right, associated with your table. So another lookup might need to be done. So there are a lot of writes when you on just there can be multiple writes on just one write in your database, right? So fsync and fdata are synchronous operations, and disk writes are take long. Then how database perform fast with high CPU operations without compromising on efficiency and reliability. So would you say that in order to just make sure that I'm writing everything, I'm always going to fsync? Because if I'm going to fsync, it is going to take me longer because I'm going to wait. I'm not going to asynchronously write it. I'm going to make sure, because disks are slow, right? So I'm going to wait for the disk to write everything down. I'm not going to write to the OS page cache because it will be faster. I need to go slower because I need reliability. But if I need reliability, then and I need to make sure that everything I'm writing onto the disk gets there, and I'm always doing a synchronous operation, then my writes will be very slow. My database will just die just trying to write everything, right? Here comes the concept of write-ahead log. So what a write-ahead log tries to do is that what databases do, that they, whenever you create a record, let's say you insert one record or you update one record, they have databases load their already load their tables into the memory, right? And what they do is they update, they update the table inside of memory, inside their buffers in the memory, and they write one log, just one log, on the updates that they've done. That's it, right? So what it does is that now your actual data is present in memory, and it has been written via fsync to the log file, which we call write ahead log, because we are writing ahead. This is a write ahead log. What does write ahead mean in this case? You are gonna write to the table, which is going to persist on the disk, but you're not writing to the table. You are writing on the disk. You are avoiding that write to the table on the disk, and you are updating the memory table that you have that the database has already loaded. So it is fast because it is only updated in the memory. And now what it does is it just creates a log entry that I have changed this to this. Right. So it is the write operation is very small, and it knows what it has changed where. And the log by structure is what? An append only thing. So you have an order of things that your database knows that what it has done. So in this case, let's say your database actually fails, and that data which was written onto the memory in the memory table was not actually flushed down to the disk, but had ensured before communicating to the client that the data is written in the write-ahead log. It was very small price to pay. So what it does is it loads up all the data in the table into memory. When you restart that crashed database, it loads up all the data in the database into the memory. Then it replays the write-ahead log from the beginning, and it updates all the transactions, all the operations that it had written, that it has done this, and it replays all those operations again onto the memory table. So the state is now back to what it was before the crash, and it is reliable.
So what about redundancy? If let's say it replays the log file and there are some updates over there or creation file, then won't it be a replication of data or something like that?
No, because redundancy you are talking in terms of replication or replication. So replication can happen in two ways again, synchronous or asynchronous, right? So if it is a synchronous replication that you have enabled in your database, what it will do is, and how many replicas have you configured your database to synchronize to? So what it will do is, it will ensure that all of the replicas that you have configured or that you to replicate synchronously, it will wait for all of them to write to their write-ahead log and modify in their in-memory buffers, and then return back that okay, I have written. And if it is an asynchronous, then it will just write onto its memory and its write-ahead log, and then revert back that okay, I have written. But it will not be replicated because it will be replicated asynchronously. So synchronous writes are always better, but they come at a cost, right? The price of consistency is actually latency, right? Okay. So different storage solutions refer to this mechanism, write-ahead log, by different names. So Postgres, what it calls is write-ahead log simple. CEF, storage defined, software defined storage. Has anyone heard of this software defined storage, CEF cluster? No? Okay. One, okay. RabbitMQ, most have heard of it. It also maintains a write-ahead log to ensure that all the messages are written to the write-ahead log, and if it crashes, then no data is lost. MySQL calls it bin log. ElasticSearch calls it transaction log. Translog also, some people say. MongoDB is also calling it transaction log. Neo4j as well. File systems, ext4, XFS, they call it journals. So you must have heard of that. What XFS is, what ext4 is. It is a journaling file system. What journaling file system is actually doing is, it is writing a log with fsync. It is updating it, the data in the page cache, in the memory, and then it is just communicating that I have written, right? Append only file system in Redis. There is an RDB also, but it is not this mechanism. It is different. In Cassandra, we call it commit log. In Oracle, we call it redo log. Redo log, why? Because when the database starts up, it will redo all the log from the beginning. It will replay, right, after loading the table into the memory to get back its state when it crashed. Get back to that state. Okay, what problems have we solved for create, update, and delete? Fsync and fdatasync solved my reliability problem. If my systems are failing, then I don't care because I'm ensuring that my data is being written onto the disk via the write-ahead log mechanism, right? So write-ahead log solved my efficiency in writes because I'm not writing everything. Yeah, exactly, because they are using the write through mechanism. They are not using the write back mechanism. It is a kernel syscall. So in order to there's one more thing. So in order to ensure that the data has been written to the disk, the storage layer, which is SSD or hard disk drive, their controller also needs to be compatible with the syscall mechanisms. And most storage solutions these days, what they try to do is enterprise grade storage solutions I'm talking about. They try to be compatible so that whenever a kernel issues fsync call, the controller, honors it and flushes everything in its cache onto the disk. Because the fsync call would need to be understood by the storage controller, right? Somehow. There is a different mechanism which is called in storage controllers. It is something, but yeah. Can you have some mic? You can come ahead now.
I just said, like, controller of the disk will be honoring the fsync call and saving it
Yes.
to its own cache. Right?
The disk controller would be honoring the fsync call VI mechanism, I'm forgetting the name of that mechanism, that fsync integrates with the disk controller. And what the disk controller does is it honors that, okay, my writer has issued an fsync call, so I need to flush all my cache and let the write pass directly to the disk. Any more questions up until now? Okay. This is understood, I believe. Fsync and fdatasync solved my reliability problem, and vol solved my efficiency in writes, because I'm just writing small data via vol log. I'm not writing everything. I'm writing everything in memory and just writing the updates in the vol log via fsync and fdatasync. But what about efficiently organizing writes? Let's talk about storing the data on disk for efficient reads. So how the data is stored actually by the database, it has two mechanisms. LSM, that is log structured merge, and one is B-tree. Different databases use different mechanisms, but the idea is that in a B-tree mechanism, it is a balanced tree basically. So the database maintains the data structure in its memory in the balanced tree format in order to search efficiently and write efficiently. Whereas on the other hand, what the idea of log structured merge storing mechanism is that you already have written your data onto the disk via fsync in the write-ahead log. Why not use it? Right? Why are you now like updating and creating a different that data in a different format in a B tree? Just use it. No, you already have that data. So the log structured, which is again log append only structured merge, I'm coming to in a minute what it actually is referring to. But the idea is that you organize your data in different formats for different purposes. So for B-tree, the reads have to be fast. So if your storage mechanism is using B-tree, you will be optimizing it for reads. If you are using LSM, the log structured merge, you'll be optimizing your system for writes, because you are just writing append only ahead, right? There is no lookup, because B-tree will be having a lookup involved, right? Okay, a word about indexing. So when you create this data format, you keep this format in you keep this data in this format. You need to be able to search it efficiently. But you have organized everything, all of your data in this format. But it is it is a very dense data. You need to be able to have a lightweight data which you can read fast and then search it. So those are the those are what indices are. You create a lightweight data storage based on your needs, based on the type of data that you have. Maybe you have a date timestamp, so you'll create a date timestamp index. If you have a textual, you'll create a different, maybe and all of those indices work differently, right? So back to Elasticsearch. Any question up until now in the storage layer mechanism? What it does and how it works, how it fails, when the systems fails, how it operates. Any questions? Okay. So Elasticsearch has multiple storage layers. There is segment files, there is shards, there is index, there's alias, there's data streams. So shards, we understand, those are the actual Lucene indices which hold the data. Indices are an abstraction on top of this these shards, which collectively mark one data set. That these 3 shards are collectively index 1. These 5 shards are collectively index 2. Alias, the concept of alias is that because you are just writing your latest data to the indexes, keep writing it. How will you manage deletion of data. So I need to take care of only maybe, let's say, I need to store in my ES just last 7 days of data, right? But I'm only writing to this one index. And how many of you will say that deleting records in a table is the way to go if you want to clean up your data in the database? Raise up hands. What is the other mechanism? Anyone? Partitioning, right? So you write your data into specific partitions in RDB is what I'm talking about, not in terms of ElasticSearch right now. You write your data in partitions and you create partitions each day. And what you do is you just, on the 7th day, you just drop that partition. So it just frees up your data. And you must have heard about the vacuuming, what vacuuming does in databases, if someone has read about it. It just, whenever you mark a data as deleted, it does not clean up the space. It just keeps that space available for another record to make an entry after the vacuuming. In actually the relational database that I worked on, MySQL and Postgres. And it is the same in Elasticsearch as well. Whenever you delete a record, the space is not freed. So if you created an index of 10 GB and you inserted 1 million documents in it, and you now want to clean up the space from your disk, and you go about deleting those 1 million documents, and you delete all, you will not reclaim all of the storage space because it is just marking those documents as deleted. So if you want to reclaim the space, what you will have to do is you will have to drop that index. But in a working environment where the data streams are coming in, where your data is flowing in, how will you be able to delete that index? So what Elasticsearch has done is it has created another wrapper on top of index. So there is another wrapper on top of index, alias, and then under alias there are index. So whenever you want to write or you want to read, you want to write to the alias, and behind that alias, whichever index is read-write index at that point of time, your writes will be routed to that index. And whenever you want to delete it, if you want to delete it, you want to manage your data, you roll over it, you rotate it. So you create a new index and you attach it beneath this alias. And you mark this index as read-write index. Now, so the old index becomes read-only. So no writes are being forwarded to this old index. All writes are now forwarded to this new index. Next day, new index. Read-write, old one, read-only. So now for each day, you are creating new indexes. And on the 7th day, you can drop off the 7th, the 8th, 7 days back index. So once you drop it, your space is freed. You do not have to wait for the space to be freed. Data streams is another mechanism that Elasticsearch has provided. So the thing was that it could happen that you will be writing your, most probably, you will be writing your logs to Elasticsearch. But the thing was with alias was that you could update. So if you have a read-write index beside this alias, you could send update requests to this read-write index. But if you have just log data, you do not require updates. You do not want to manage the hassle of just maintaining your indices with ILM policies that roll it over and then delete it. You just create a data stream. It is going to be just append only. No updates are going to happen, and it will manage indices on its own on the backend. No policies required. Segment files. So a shard is a Lucid index, and in shards there are segments. Segments are nothing but a sequential record of your data, and one shard can have multiple segments. It's not like one shard is corresponding to only one segment. It can have 3, 4, 5, 6, 7 segments. Each segment is a sequential write-only record, and whenever you want to, whenever Elasticsearch wants to free up the space. So I was talking about that if you delete your records, it will just mark them as tombstones. It will not clean up the space, but it has to create some mechanism so that it creates some space for moving forward. So that the space gets freed up. So once your documents have been marked as tombstone, marked as deleted, in the backend, there is this process in Elasticsearch that keeps on running, which is a merge process. What merge is doing is, so you're writing your records in different segments in this index, in this Lucene index, shard, and once this process identifies that, okay, a lot of data has been deleted from, a lot of records have been deleted, documents have been deleted from this shard, I need to clean up some data to free up some space on the file system. So I need to merge multiple segments into one, so that in one segment there were 100 records and 60 of them were marked as deleted. In another segment, there were 200 records and 100 of them were marked as deleted. So you are effectively wasting 100 plus 60 documents of space. So this process, what it does is, it creates a new segment, it merges these two segments, picks up 100 which were not deleted, 40 which were not deleted, and writes it to the new segment. So the new segment has 140 records without any tombstones, and your space is free. Your space is freed up. Okay. Components in Elasticsearch storage. So we have in-memory buffers, which is the point where I was talking about that you write your data in the memory and you write it to the write-ahead log. So the in-memory buffers provide you the way. Yes.
Regarding alias and indexes, I believe I read somewhere that we can use like alias can point to multiple indexes.
Yes.
How does that work? Can you elaborate on that?
One alias can point to multiple indices. Only one of them would be read-write index, and all others would be read-only. So that whenever you send a write CUD, create, update, delete request to this alias, only the read-write index will receive that query.
So how will that efficiently help the retention policy or a particular?
Because you are writing only to the current read-write index, and you can create new index and to associate it to the alias. So new index will become read-write, and as the new indices get created, the old indices you can free them up after some time. So the old indices were read-only, no. So you do not require that 7 days old index to take up your storage space. So you can just drop it off with the policies. Any other question? Okay. So in-memory buffers are the things where when I was talking about that data is being updated to write-ahead log, and also in the in-memory page cache. So the in-memory page cache, it has some data structure. The application is maintaining some data structure. Application in this case, Elasticsearch, right? So it is maintaining its data structure in the buffers. The buffers are just append-only files. Yeah. The segment files, they come in two flavors. One is the committed segment files, and one is searchable segment files. So when you're writing these segments, you're writing data, you're writing actually to the segments in the in-memory buffers. But what happens is, if you want to get those data to the storage, it will be flushed, and it will take some more hit from the storage layer. So what Elasticsearch did was, it created a lightweight sort of fsync. What it does is, it the segment files which were in memory, which were actually in memory, the data which was actually in memory, it flushes that data and it creates a segment file in memory only. It has not been flushed down to the disk. It is right now residing only in memory, but the transaction log is still there, written to the disk. So whenever you then create what was that called? I forgot. Flush. Whenever you create flush, so just now, you flush that in-memory segment back to the disk. So you refresh. This is called a refresh and flush. So when you refresh your data from the in-memory buffers, which was not searchable as of yet because it was in buffers, it gets written to an in-memory segment file, and that in-memory segment file is now searchable. And that in-memory segment file is being created every 1 second because refresh happens every 1 second. So you have a lot of in-memory segment files which are not committed yet at the time of whenever you are writing new data. And when you have to write those in-memory segment files to the disk, what you do is you merge all of those segments into one segment so that you can have a bulk write onto the disk, which is efficient. Make sense? So what it tries to do is it tries to buffer a lot of data and write requests in bulk so that the disk storage does not take a hit because disks are again have a lifetime of in reads and writes. So you can only read and write onto the disks up until a certain threshold. So after those, it fails. So it is better to have bulk writes, which are less, and not have multiple writes. So this is why databases try to optimize and write in bulk. Segment files merge. So I've explained it, what merging actually does. Tombstones, we already covered. Data flow overview. The write path looks like this. Client sends an HTTP call, might be a GET, might be a PUT. In this case, this is a write path, so this is the PUT request. The coordinator. So the good thing about distributed systems is, when I was talking about, is that you can contact any node and all of the nodes would behave the same, right? And because all of the nodes have just one motive, to get the task done for the client, whoever has contacted them. So if the data does not, if that node does not have the data, it will communicate to another node to fetch that data. Or if the request is for write, it will communicate to another node where the data shall be allocated, shall be written to be written. So the coordinator node can be any node which the client communicates to. So you have 10 nodes. If the client communicates to third node, it becomes coordinator. If the client communicates to 10th node, it becomes the coordinator. And it coordinates writes and reads further down. So ingest pipelines get triggered. Ingest pipelines are nothing but what needs to be done if if the database gets this kind of document. The data node gets the data, which would be the primary the primary shard, and on which the data node on which the primary shard is right now allocated will receive the request to write that data, because primary shards are allocated to nodes. Once that data is received by the primary shard on one node on which it has been allocated to, it parses it for indexing, text, analyze, it buffers it, and then flushes it. So this buffer is referring to the in-memory buffers. In the backend, it will be refreshing, writing it into the memory new segments every second, and then flushing it onto the segments which we call commit. There's a read path overview. So the client sends a query onto any node. It has sent to node 2, so node 2 becomes the coordinator node. If it had sent to node 3, it would become coordinator node. So node 2 becomes the coordinator node right now because it receives the query, and the node 2 knows where to route the request to, because it knows to which shard has been allocated to which nodes. So it forwards the query to all the nodes for the query to be executed on all of the indices in parallel, and all of the segments in them in parallel. But the searches in segments happen sequentially, because those are just written sequentially. Okay, refresh we have covered, can be thought of as a lightweight fsync. It just creates new files and makes them searchable. In memory, those segments are written. Happens every second in Elasticsearch. Flushes the in-memory buffers. Sorry. It flushes the in-memory buffers to create an in-memory segment and allows it to be searched. Flush, an actual fsync to merge the segments and flush the merged segments onto the disk. Refresh and flush in the diagram way look like this. You have you are writing everything to in-memory buffer. You have commit points which are searchable. The refresh happens. In-memory buffer is flushed. It creates a new in-memory segment which is not yet written down to disk. So it is not yet considered as committed. So it is, but it is searchable, right? So next. Another diagram to explain it. I just wanted to make this point clear. So what refresh does is, again, document is being written. It gets written to the translog, write ahead log because of safety. It gets written to the memory buffer. Buffer contents copied to newly created segment, which is again in memory. This was refresh and this is flush. So you have in-memory segments. You have data in translog. You have you create a new merge segment, you flush it down to the disk, and translog gets empty. Yeah. So we have not covered this. So once you have your data written to translogs and you have updated it into the in-memory data structures, would you just keep writing and appending to the translog? Because you were writing to the translog for some reason, no? You were writing to the write-ahead log in order to be reliable. So you need to flush that data out because you will not just be appending to it. You have not written that data down to the disk. So once the background writer processes flush those in-memory changes, which are dirty pages, once those dirty pages are committed down to the disk, the translog serves no purpose. So the translog, the write-ahead log is then cleared. This process is called checkpointing. So I have not mentioned it right here. So yeah, any questions up until now? Am I overdoing? Okay. So once you have written to the write-ahead log and very small data, and you have updated all those changes into the memory page caches, you will now have dirty pages which are not yet written to the disk. Those are written to the write-ahead log, but your queries do not search the write-ahead log. Your queries search the actual database. So once you receive the queries, your database for the newest queries, data for the newest queries, your database will return the data from the dirty pages, which just currently reside in the in-memory. They have not been flushed down to the disk on the table. Right? What has been flushed down to the disk? A log of what changes have been modified into the memory. So there is a background process that happens continuously, which flushes down the dirty pages into the in memory down to the table. It writes everything down because it takes longer. There can be multiple writes for one write. No, so you wrote everything down in memory because it was fast, and now you will take your time to write down all the changes onto the disk. You do not care because you have written all the changes to the transaction log. If your system fails, it comes up, it will load the database, it will replay the write-ahead log, and your system will be back to its state before when it was crashed. This process is called checkpointing, when your dirty pages are being flushed down to the disk. And so the write-ahead log serves no purpose in that case. So because your all dirty pages have been flushed. So write-ahead log can be pruned, can be truncated, right? So this is what databases do actually. Any questions? Sorry.
So I'm not very sure what write-ahead logs are. So are they actually a file?
Yes.
File
Yes.
So if it's a huge file,
append only.
append only. Like
Yes.
now, whenever the checkpointing happens,
Yes.
it needs to remove all those which are below that, right? So not
Above that.
above that, right? So does it keep a
Track.
yes?
Yes.
Does it keep a track of
Yes.
removing all those?
Yes.
Okay.
There was one more person who had a question.
Hello. Two questions. One, how any node act as a coordinator node? Like, does it have the index of shard saved? Like, how that thing is synchronized between the nodes, that which shard has which index of data, right? So there's no master coordinating. Where should the request be routed to, right? And in-memory segments, like, are they flushed out or they are just discarded?
They are just discarded. Tombstones in the memory are just whenever they are in the memory. So before the flush happens, which is creation of a merged segment and then flushing it down. Before the flush happens and the new segment is created, merging all of those in memory segments. The tombstones are ignored and the new segment is created without the tombstones. And then the tombstone free segment is flushed down to the disk. And regarding the coordinator thing, so data nodes do not have are not marked as master or slave. The metadata nodes, the nodes which keep the metadata are marked as master or slave. So um, each shard becomes a primary or a replica, but there is no data node that is assigned the responsibility of master for this data. The responsibility for the master in the Elasticsearch cluster is to manage the metadata synchronously, so that everyone can be in sync, that which nodes have what data, which nodes have been allocated what shards. So this happens via the gossip protocol in Elasticsearch. So each of the nodes continuously try to communicate with each other in order to make sync, and they communicate with the master. Any other questions? And coordinator node again. Any node is coordinator on which the request has landed. Any node becomes the coordinator. Distributed systems. And all the nodes have the same responsibility to serve you consistently. Does not matter which node you communicate to. Indexing and index are not the same. Understanding the context. Okay. So we talked about index as in the logical abstract which combines all of the data shards in under the one umbrella. But indexing refers to writing to two things. One, writing the documents into the index, which will then get written to the shards and down to the segments. But indexing refers to one more thing, which is creating the actual indices, which are lightweight data structures, which databases can query for to optimize for reads. Like we have in relational database, we call indices on tables, no? So in here we also call like them indices. So it is just a bit, I don't like the naming of it, but okay. Types of indexing, field can have text for full search, keyword for exact match. For full search, full text search, we mean to say that you can search anything. So you can search in case insensitive manner and everything would be searched for you. But for keyword search, the case sensitive things matter. All of the text in its order, in its state matters. Every letter, every spacing. So whenever you want to have aggregations, you would go for keyword indexing, and whenever you want to just search something, you would go for the text indexing. अंडरस्टैंड कितनी स्लाइड्स बची हैं बहुत हो रही है यार कोई बोर हो रहा है तो मैं छोड़ सकता हूँ. Okay. Sorry. Understanding how the R works in CRUD. R refers to read. So how, yeah, just 5 to 10 minutes more. So how reads work is Elasticsearch clients are querying to alias, and those aliases are routed to all the indices. The indices divide the query either write or read into the shards, and then shards are the actual thing which write the data to the segment or read the data from the segment. So this is how actually reads work in context of a very simplified explanation. The gossip protocol was the thing that you were asking, how nodes communicate each other, how they know which nodes are in the cluster, which are not, which nodes have allocated what shards. That is done by gossip. Coming on to queries, maybe if you want to query an Elasticsearch cluster, you want to be able to understand the structure of the URL. We have scheme, HTTP, HTTPS, subdomain, the part, the path, the query parameters. Fragment is not required, but query parameters are different. So if you can go down and read the documentation of Elasticsearch, it is just RESTful APIs, everything. So you can just use the REST APIs understanding to query the database. The different APIs, not the database, because the database requires different the understanding of its language, query language. Just examples of few HTTP APIs. We have cat indices. So this is my HTTPS request to this node on this port. The API is cat indices. The parameter I'm using is V for showing the headers. In it, you will see docs count and docs deleted. Docs deleted are 0, which means there are no tombstones in this index. If there were any tombstones, maybe you updated some record, so the old record would get marked as tombstone and new record would just get inserted, or maybe you deleted, those would get incremented. Primary represents the number of shards and replica represents the number of replicas for that individual shard. So replica 1 represents that both two primary shards have one replica each, and it is green in status, so which means that all the replicas are up. So there is no replica that is down. If it would have been yellow, then it would have meant then that at least one replica is down for this shard, for this index. For the shard, for any shard of this index here. Cat aliases shows your alias and your indices behind it. Is right index, you can see only one index can be true, can be read write index. Other indices have to be read only. So other indices are marked as false in the is read write index. Cat nodes API shows you all the nodes of the cluster. Master, there are 3 master eligible nodes. Out of those 3 master eligible nodes, yeah, node role. So out of these 3 master eligible nodes, 1 is right now master. All of the nodes are eligible to host data. Allocation tells you how many shards each node has, what is the amount of total disk space used, and yeah. Cluster health. This represents, so the 2 fields are important in here to understand. Unassigned shards and initializing shard. And straight green just means that all of the shards and all of the replicas for all of the shards are right now up. There is no replica of any shard that is failing or is down. If the cluster would have been in yellow state or in red state, the initializing shards and unassigned shards number would not be 0. The unassigned shards represents how many shards are there right now in the cluster which have not been allocated to any node, which means that the data is not yet available to the client to query. Initializing means that, so when we talked about that if a system has failed, it will recover whenever it starts up, it will load the data into the memory, it will replay the write ahead log. So what initializing means is that the shard has been allocated, now it is coming up. So the data is being loaded into the memory, and the transaction log is now being played. So it is initializing. It is not yet ready. It is initializing. Other helpful APIs in Elasticsearch recovery shows you the how much percentage has been recovered in the initializing state. Thread pools, settings, shards, segments, all representing different things. What about managing large scale data, tiered storage? So if you want to have your cluster organized into a set of nodes which have hard disk associated with them, so they will have less IOPS. So you can organize your old data on them. You can have the latest data, the current data onto the nodes which have SSD associated with them. So you can create tiers, hot, warm, cold. So your data keeps on moving from one tier to another tier to another tier, and the performance of your querying reduces as the data moves from tier to tier as the time progresses. Searchable snapshots, you can remove your data from Elasticsearch cluster and you can upload the snapshots onto the S3 storage layer. And what Elasticsearch allows you to do is, it allows you to mount those snapshots onto your cluster. So your cluster, the shared nothing architecture, does not hold any data. The data has been offloaded to the outside storage, which is S3, and you can just mount those storage volume, mount that storage and use it to query that data. Index priorities. So if you want to have the latest indices recover as fast as possible, you will put them as the highest priority, because recovering, if a failure happens, then recovering the oldest data as soon as possible does not matter anything to you. You want to recover the latest data as soon as possible, not the oldest data. So you mark the oldest data as the least priority and the latest data as the highest priority to recover the latest data as fast as possible. ILM is just index lifecycle management. The policies which you create for the indices to get rolled over and deleted. SLM is snapshot, so you can take snapshots in intervals. And this is my sign off. Yeah. Any questions? Yeah.
How the read time will be covered in short, but indexes when you have it, you only. So indexes you explained that there is only one read and write, and the other ones are only read only. So during the read only indexes, do they help in improving the efficiency, or they are used?
The read-only indices hold the data in memory to be able to serve the queries.
Yeah, so that would be increasing the efficiency of the read.
Yeah. Any other questions? Okay. Thank you.